Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Saleh Ali, and today I will talk about the third chapter of mechanical vibration, which is harmonically excited vibration. And this homework will be under the supervision of Dr. Fibriyan Ahmaduddin. All the information of this presentation will be taken from the book of Mechanical Vibration by Singers US Raw. In this presentation, inshallah, we will cover a lot of things. First of all, the introduction of the third chapter. Secondly, we'll talk about the equation of motion for the forced vibration. Thirdly, we'll talk about the response of undamped system under harmonic force. The fourth topic will be response of damped system under harmonic force. And then we will talk about the response damped system under this equation, which will be represented as a complex form. And we will talk about the response of damped system under rotating imbalance. Then we will talk about the self-excitation and stability analysis. After that, we will talk about the transfer function approach, and then we will talk about the solutions using Laplace transforms. And there are a lot of topics in this chapter, but we'll focus on these topics, inshallah. The topic we'll talk about is the introduction of this chapter. Forced vibration happens when external force or displacement affect the system. If this excitation is periodic, it leads to harmonic response. Otherwise, it results in transient response. The system's response can be described using harmonic excitation equation involving amplitude, frequency, and phase angle. And the amplitude, as we see in the equation, is the F naught. A key concern in the vibration analysis is the resonance. When the excitation frequency aligns with the system's natural frequency, leading to dangerously high oscillations to prevent failures. Engineers carefully design systems to avoid resonance. And there are a lot of real-world examples, like rotating machine and vehicle responding to uneven road surfaces. Now we will talk about the equation of motion. The equation of motion for a forced vibration system follows Newton's second law. For a single degree of freedom system, it's given by mx double dot plus cx dot plus kx equal to f of t. Here, mass, damping, and stiffness determine the system's behavior. The solution consists of two parts: the free response, which depends on initial conditions, and forced response, which depends on external excitation. And for free response, the solution will be homogeneous, and for forced response, the solution will be particular. Here, as we see in the figure 3.1, it's a spring mass damper system. This figure shows a spring mass damper system where a mass is connected to a spring and a damper. When an external force, as we see F of t, is applied, the system responds according to the equation as we said before, the equation of mx double dot plus cx dot plus kx is equal to f of t. The free body diagram highlights the forces acting on mass, which is the restoring force from the spring and damping resistance and the force applied. And in figure 3.2, as we see, the system response over time. And this figure illustrates how the system's motion evolves. The total response consists of homogeneous solution, which is free vibration that fades over time, particular solution, which is the steady-state response due to the external force, and a general solution, which is a combination of both the homogeneous and the steady-state response, where transient motion eventually disappears, leaving only steady-state oscillation, as we can see in these three curves. The first one, xh of t, which is the homogeneous solution, and secondly, xp of t, which is the steady-state response, and the x of t is the general solution. And now we will talk about the third subtitle, which will be the response of undamped system under harmonic force. First of all, the equation of motion for undamped system will be simplified to mx double dot plus kx is equal to f naught cosine wt. Unlike damped system, there is no energy dissipation, so transient vibration persists indefinitely. And for the general solution will be the total response combined the homogeneous solution, which is free vibration at Wn, and the particular solution, which is the forced vibration at W. And the steady state amplitude, which is denoted by capital X, depends on the frequency ratio, which is R. Notice as R goes to 1, X blows up. The third thing in this subtitle will be the resonance. When the frequency is equal to natural frequency, the denominator 1 minus R squared becomes 0, and our particular solution breaks down. Instead, the amplitude grows linearly over time. So we should care about the resonance for these systems. And the engineers must ensure that the frequency not equal the natural frequency in undamped systems, for example, including turbine blades or bridge without dampers. In reality, damping added to mitigate resonance, but studying undamped cases help us understand worst-case scenarios. In figure 3.3, we can say magnification factor versus frequency ratio. The plot shows how the amplitude ratio changes with the frequency ratio. And at r equal to 1 will be the resonance. The amplitude theoretically become infinite. And if r is less than 1, the case will be subcritical. The amplification increases gradually. And if the frequency ratio is greater than 1, the case will be supercritical. That means the amplitude drops and the response flips phase. Designers and engineers should avoid that the frequency ratio is equal or near to 1 to avoid resonance in the structures and machines. And the magnification factor quantifies how much vibration amplified due to the dynamic forces. And now we will talk about the beating phenomenon. If the forcing frequency is close but not exactly equal to the natural frequency of the system, a phenomenon known as a beating may occur, as we can see in the figure 3.8, how the amplitude rises and falls smoothly over time. The peaks of envelope correspond to the moments when the forcing and natural vibration reinforce each other, while the troughs occur when they cancel out. This pattern repeats every as we can see, 2 pi over the frequency. So making the beating phenomenon is a predictable yet critical phenomenon to manage in mechanical systems and for good designs. Now we will talk about the response of a damped system under harmonic force. Unlike undamped systems, damped systems under harmonic forces avoid infinite resonant amplitudes. For example, think of a shock absorber in cars. Damping smoothens the ride by dissipating energy. And here, as we see in the equation of motion, the difference that there is a damper, which is C. And of course, we will have damping ratio, which is zeta, that control energy loss. The steady state response or the particle solution depends on R and zeta, the magnification factor X and the static deflection at when X near to R is equal to 1, but the damping ratio flattens this spike. And there are some figures, we'll see it inshallah after this slide. And here we can see the homogeneous solution, and to find the total response we should add the homogeneous solution or the particular solution. And there are a lot of examples in our life for damped system under harmonic force. For example, car suspensions, of course the car using the damping to respond to road vibration. Similarly, skyscrapers employ tuned mass dampers to counteract wind-induced oscillations. And that's why we should always design the damping system that have zeta and natural frequency to keep the frequency ratio, which is R, away from the critical ranges, so we can avoid resonance. As we see in the figure, there are two parts. The first part is the magnification factor, which is M is equal to X over the static deflection. As we see, as R is equal to 0, each static force M will be equal to 1, the system deflects statically. And near R is equal to 1 will be resonance. For undamped, zeta is equal to 1, and M will go to the infinite amplitude. For damped, zeta greater than 1, the peak M decreases sharply with higher zeta. And if the R is greater than 1, that means high frequency excitation, and M will go to 0, and the system cannot keep up with the force. So we can understand that damping is critical to suppress resonance. Even small zeta, for example 0.1, reduce M by almost 80% compared to undamped systems. And for the part B, which is the phase angle, if R is so much less than 1, that means low frequency force, and the phase angle almost 0, that means response aligns with the force. For example, slowly pushing a swing, that it moves with your push. When the R is equal to 1, that means resonance, and the phase angle will be equal to 90, and response lag the force by the quarter cycle. If they are much greater than 1, that means high frequency force, which is the opposite of low frequency force, and the phase angle will be almost 180, which responds opposes the force, that means out of the phase. And the phase angle graph is very important because the phase shift helps diagnose vibration issues. For example, when the phase angle have a sudden change to 90, that means signal resonance. The section 3.5 is the response of a damped system under the complex harmonic forces. By representing force like f of t is equal to f naught e to the power I frequency multiplied by t, we simplify solving differential equation using complex number. And as we see in the equation of motion, we have the same contents, but the equation will be equal to f naught e to the power I multiplied by frequency and time. And I it's a representation of a complex number. And for the particular solution, we assume steady state solution where x is a complex amplitude, as we can see in the equation. And now we'll talk about the complex frequency response, which combines magnification and phase lag into one expression. The magnitude of complex frequency response is the familiar magnification factor from the previous section, which is 3.4, and the phase quantifies how much the response lags the force. For example, at resonance, that the frequency is equal to the natural frequency, we'll have the phase angle will be equal to 90. And we will see, inshallah, in the next slide, the figure that visualizing the displacement and velocity and acceleration as rotating vector in the complex plane. The complex frequency response are used in many applications. For example, to design vibration isolators and filters. And also, it's used in audio system. The frequency response determines how speakers handle different sound frequencies. You see in figure 3.13, it visualizes the harmonic motion of a damped system using rotating vector in complex plane, and in simplifying the equation of motion. Each force, mass, acceleration, damping, and spring stiffness is represented as a vector rotating at angular velocity. The mass acceleration leads displacement by 180 degrees. The damping force leads by 90 degrees, and the spring force aligns with the displacement. The third vector balances the external force projected into the real axis for physical interpretation. The diagram clarifies phase relationships and dynamic force balance, aiding engineers in tuning systems to avoid resonance or excessive vibrations. And now we'll talk about the response of a damped system under the harmonic base motion. It occurs when the base of a spring mass damper system oscillates sinusoidally. The system's equation of motion considers both the damping force and the restoring force, leading to a steady state response, as we can see in the equation. And it depends on the frequency ratio and the damping ratio. The solution shows the response amplitude is influenced by the displacement transmissibility, which determines how much of the base motion is transmitted to the mass. At low frequencies, the displacement transmissibility remains close to the unity, meaning the system follows the base motion. However, near resonance, when the R is equal to 1, the resonance can become significantly amplified, especially when the damping is low. For higher frequency ratio, smaller damping leads to larger transmissibility values. These principles are critical in designing systems for vibration control, such as seismic base insulation, vehicle suspension system, and machinery foundations, where minimizing unwanted vibrations is essential. As we can see here in figure 3.15, it illustrates the vibration displacement, transmissibility, and phase angle with respect to the frequency ratio. The left graph, which is A, shows how TD changes for different damping ratios at low frequencies. It's close to unity, meaning the system follows the base motion at resonance. The transmissibility can become infinitely large in a damped system when zeta is equal to 0, but damping reduces the amplifications for frequency ratio greater than the square root of 2. TD drops below unity. indicating that the system moves less than the base. The right graph, which is B, shows the phase angle, which represents the phase lag between the system's motion and the base excitation. The phase shift increases with R, approaching 180 degrees at high frequencies. The damping ratio significantly affects both transmissibility and phase response, making it crucial in vibration isolation applications. Now we'll move to the next subtitle, which is the response of a damped system under rotating imbalance. It occurs when a rotating component, such as a disc or rotor, has unbalanced mass, generating a periodic force due to the centrifugal effect. The equation of motion for such a system included mass damping stiffness term, along with an excitation force proportional to the square of the rotational speed, as we can see for the equation of motion. The steady-state response reveals that the vibration amplitude depends on the system's parameter and the excitation frequency, reaching a peak near the natural frequency, which is the resonance. For the phase angle, it determines the lag between the system's motion and the excitation force. Varying with frequency at low frequencies, the system follows the excitation closely, while at resonance, the response is amplified significantly, especially when damping is low. At high frequencies, the displacement decreases, and the system moves out of phase with the excitation. This analysis is crucial for designing rotating machinery to minimize excessive vibration and ensure stable operations. And now we'll talk about the self-excitation and stability analysis. First of all, self-excitation occurs when the system's motion feeds energy into its own vibration, causing instability. For example, the brakes equal and flutter in aircraft wings. Stability is determined by analyzing eigenvalues of the system's equation. Positive real parts indicate exponential growth, as we can see in the equation of stability. For instance, a spring mass on a moving belt becomes unstable if friction decreases with velocity, creating negative damping. And that's it for dynamic stability analysis. Now, for flow-induced vibration, like those from vortex shedding, they generate periodic forces. The shedding frequency tied to the Strouhal number, which is almost 0.21. The risk of resonance if matched to a structural natural frequency. And mitigation includes dampers, for example, stuck bridge dampers on power lines, geometry changes, and ensuring that it avoids critical frequencies. Proactive design prevents failures, emphasizing stability check and energy distribution. Now we'll talk about the transfer function approach. As we can see, this is the equation of transfer function. It's the mathematical backbone of linear system analysis, defining how input like forces translate to output like displacement in systems such as mass spring damper. The transfer function of a system is specific yet structure agnostic. Identical function can describe vastly different systems from car suspensions to electrical circuits. It derived via Laplace transforms. It simplifies differential equation into algebra, enabling engineers to predict response to any input and identify resonant frequencies or reverse engineer unknown like damping or stiffness through experiments. By applying a known force and measuring vibration, the transfer function bridge theory and practice underpinning everything from aerospace stability to noise-canceling headphones. Its elegance lies in transforming complex dynamics into a universal tool for control testing and innovation. And also, as we see in figure 3.35, the transfer function can be represented as a block diagram where the input and output are shown in the left and right side, respectively, of the block with the transfer function shown inside the block. And note that the denominator of the transfer function is identical to the characteristic polynomial of the differential equations. And now we'll talk about the solution using Laplace transforms. First of all, we take the Laplace transform of the input force as we see in the first equation, and then we use the transfer function as we can see in the second equation. And when we multiply the input force and the transfer function, we get the Laplace domain response. And to convert it back to time domain, we decompose the Laplace domain response using partial fraction after applying the inverse Laplace transform. The transient terms decay to zero over time, as we know, because e to the power minus zeta natural frequency multiplied by t will decay to zero, leaving only the steady state solution as we can see it in the third equation, and it's simplified this form. And the phi is the phase lag caused by damping. The amplitude depends on how close the frequency is to the natural frequency, and the damping ratio shapes both the decay rate and phase shift. This method elegantly isolates the perpetual oscillation we observe in harmonically driven systems. And the steps we were used is that the Laplace transform of f of t is equal to f naught cosine wt, and then multiply the input force by the transfer function to get the Laplace domain response. Then, by partial fraction decomposition and inverse Laplace transform, we get the transient term vanish, and there's only the steady state remains. And that's all for my presentation for this chapter. Thank you for listening, and I hope the information I provided is helpful. Assalamu alaikum wa rahmatullahi wa barakatuh.